In this video, we are going to review what are known as the four fundamental spaces. And this is in theory material that you've seen in some linear algebra course, but what we're going to do here is extend what you learned to the case where the matrices might have complex values. Anyway, at some point you learned about the column space of A. And what is the column space of A? Well, if you're given a matrix A, it is the set of all vectors that you can create by taking linear combinations of the columns of A, hence its name. And of course, vectors that can be created as linear combinations of the columns of A can be identified as all vectors that you can create by doing A times some vector X. Okay, so it's the set of all vectors Y such that there exists an X where A times X is equal to Y. That's the column space. And then the null space is another space that you ran into, and that's the set of all vectors X that map to the zero vector when you apply matrix A. So it's the set of all vectors such that A times X is equal to 0. And then another space that you found was the row space of A. And the way I like to think of that is if you multiply a matrix A on the left by a vector, a row vector, then what you're doing is you're taking linear combinations of the rows of A. That, of course, is a row vector. The row space of A consists of column vectors that can be created by taking linear combinations of the rows of A when you view those rows as column vectors. That's what this here says. And obviously, the row space of A is equal to the column space of the Hermitian transpose of A, or the transpose of A, whichever you prefer. Okay? And then finally, there's one more space, and that's known as the left null space of A. And that's the set of all vectors such that if you take it as a row vector and multiply it times A on from the left, then you end up with the zero row vector. Okay? And these are known as the four fundamental spaces. Now, some properties that you learned along the way was that if A times X is equal to B, if this actually can be solved, then B must be in the column space of A. Okay? If you find such a solution and then you add a vector in the null space of A to the solution X, then again you get B. If A times the Xn is equal to 0. What you're going to do next is do a few exercises that help you remember what these spaces are, and that also help you determine that certain spaces are orthogonal to each other. And that then will allow us to create a picture that kind of summarizes how matrix A maps vectors to other vectors.